A warship does not simply vanish from the surface of the ocean without a cascading sequence of fatal physics. On June 1, 1676, a single aerodynamic miscalculation set the physics in motion, past the point of recovery. A massive, top-heavy vessel attempted a high-speed maneuver under excessive sail area. The aggressive turn altered the center of gravity, shifting thousands of tons of displacement against a sudden gale. The ensuing capsize was violent enough to rip unsecured equipment from the bulkheads. In the chaos below decks, the exact ignition source remains unconfirmed. Later reconstructions have suggested possibilities ranging from an open flame to accidental sparks reaching the forward gunpowder magazine. The resulting internal overpressure likely tore away much of the forward starboard structure, or turning a capsize into a rapid breakup and sink. To understand the loss of the Swedish flagship, one must examine the precarious geometry of a 17th century floating weapons platform. The ship was a towering wooden fortress designed to project overwhelming military dominance. She carried well over 100 guns, often sighted in the range of 110 to 126, many of them cast in bronze. This immense concentration of artillery placed severe demands on stability and trim. Even with the heaviest pieces kept low, the combined weight of guns, stores, and towering superstructure left little margin when wind loading spiked. To remain upright, the hull required careful balancing of ballast and precise management of wind loading on her sails. Any sudden change in wind pressure or rudder angle carried extreme risk, but the margin for error was mathematically non-existent. The fatal sequence began during combat maneuvering in contested waters in the chaos of the Battle of Öland. The weather turned rough and gusty, applying heavy lateral pressure against the deployed canvas. Rather than easing sail early, the ship appears to have carried too much canvas for the conditions as it pushed for speed and position. When the order arrived to execute a sharp turn, the physical forces acting on the rigging multiplied exponentially. The rudder bit into the water, forcing the heavy hull to pivot against the prevailing wind. The sails acted as an enormous lever arm, translating the gale force winds into a massive rotational torque. The hull leaned violently, unable to right itself against the overwhelming aerodynamic load. Compounding this loss of stability was a critical geometric failure. Some accounts indicate the lower gun ports were left open during the maneuver. These heavy wooden hatches sat perilously close to the waterline. Their primary function was to allow the bronze cannons to fire, but an open port represents a massive vulnerability to the watertight integrity of a heavily laden hull. As the wind drove the masts down toward the surface, the hull dipped far enough for the sea to find the openings. The ocean reached the lower sills of the open gun ports. Thousands of gallons of freezing seawater rushed into the lower decks in seconds. This sudden influx of unequal weight instantly destroyed any remaining righting moment. With the righting moment gone, the roll accelerated. As the deck angle shifted from horizontal to nearly vertical, the internal gravity environment became lethal. Inside the dark, confined wooden spaces, everything that was not bolted to the primary load-bearing frames broke free. Ammunition, massive wooden gun carriages, and hundreds of men were thrown into the rising floodwaters. The internal structure of the warship became a chaotic centrifuge of falling debris. The crew faced an impossible geometry trap, crushed between flooding compartments and sheer vertical bulkheads. Deep in the forward section, later reconstructions point to a likely spark near the forward gunpowder magazine. A lantern used for internal illumination may have torn free during the roll, tumbled through the dark, and shattered close enough to matter. In that chaos below decks, an open flame or stray sparks could have reached the stored black powder just as easily. To whatever the source, inside a confined magazine ignition would have been instantaneous. In an instant, the black powder flashed into expanding gas, a pressure spike trapped inside the magazine's heavy bulkheads. The ship could repel cannon fire from outside, but it had no way to vent a shockwave born within. The blast hunted the weakest seams, splitting oak frames and tearing through planking. At the bow, the structure failed catastrophically, blown outward until the starboard foresection was effectively cut free from the hull. With the spine broken, any remaining air escaped, and nothing slowed what came next. The violently fragmented wreckage sank immediately. The ruined hull plunged through the water column, coming to rest about 26 meters, around 85 feet, below the surface, in the cold, dim water of the Baltic Sea. The instantaneous nature of the disaster left almost no opportunity for survival. Only a few dozen men are reported to have made it out. Roughly 800 were lost in the capsize and rapid descent, all in a matter of moments. The swift execution of aerodynamic failure and chemical detonation sealed the fate of the flagship, leaving a shattered puzzle on the ocean floor. The massive bronze cannons and the pulverized remains of the hull vanished into the clay, waiting centuries for a forensic resurrection. To extract roughly 60 massive artillery pieces from the clay bottom, engineers faced a brutal physical threshold. Each bronze weapon weighed up to 4 tons. In the seasons that followed the disaster, recovering that kind of mass from the cold Baltic Sea pushed early crews and their equipment to the edge. The Swedish naval authorities assigned senior officers to reclaim the most valuable military assets. The wreck lay in complete darkness, far beyond a simple breath-hold dive. Near freezing water and seabed pressure punished the body. Breaching this lethal environment required an ingenious tool known as an ambient pressure diving bell. The mechanism was elegantly simple in its physics, but terrifying in its application. It consisted of a heavy, inverted wooden cone, completely open at the bottom. Weighted heavily with lead to overcome its own buoyancy, the bell was lowered directly into the sea. As the surface crews winched the device downward, the surrounding water pressure pushed upward against the trapped air inside. The water acted as a hydraulic piston. At that depth, the ambient pressure compressed the trapped air pocket to a fraction of its surface volume. This physical reality created a tiny, highly pressurized bubble confined entirely to the upper dome of the suspended bell. The diver stood on a narrow platform rigged beneath the open rim. As the bell descended, the rising water level inside the cone forced him to climb higher to keep his head within the shrinking dry space. Once the bell reached the seabed, the diver possessed a stable, albeit temporary, refuge. He could breathe the trapped air, but the clock was immediately ticking. With every breath, oxygen levels dropped and toxic carbon dioxide accumulated in the confined space. The physical environment outside the wooden walls was entirely hostile. The jagged, ruined timbers of the warship created a maze of entanglement hazards. The water was pitch black, thick with suspended silt stirred up by the heavy equipment. Working almost entirely by touch, the diver used the bell as a staging shelter and made brief, perilous forays into the black water to locate a massive bronze cannon and rig lifting lines. Maneuvering heavy hemp ropes and iron hooks demanded immense strength and calm. Any snag in the wreckage, any shift in the bell's balance, or any failure in the lines could turn the operation instantly fatal. After successfully routing the lifting lines around the weapon, the diver retreated into the bell to gulp the foul, pressurized air. He then signaled the surface crew through a series of sharp pulls on a dedicated lifeline. Far above, men crowded the capstans and walked them around in brutal, repetitive steps. Nothing here was elegant, just leverage, friction, and muscle fighting 4 tons of bronze and the clay's grip. Under the load, hemp creaked, timber groaned, and the suction finally began to give. Over the following years, this grueling, highly dangerous cycle was executed with relentless precision. The salvage crews fought against the cold, the darkness, and the constant threat of equipment failure. Through sheer institutional engineering and physical endurance, they successfully extracted 60 of the heaviest cannons from the debris field. This massive recovery effort stripped the wreck of its primary military value. The large guns were reclaimed, but the lower decks of the shattered hull remained buried in the mud. The easy targets were gone, but the shattered hull and its fragmented secrets remained undisturbed in the darkness for centuries. For 3 centuries, the exact coordinates of the shattered Swedish flagship remained completely erased from human memory. The primitive salvage operations of the 17th century had stripped the easiest targets, but once those efforts ceased, the cold Baltic waters reclaimed the site entirely. By 1980, the tools for finding wrecks had changed dramatically. Engineer and maritime archaeologist Anders Fransson recognized that locating a wooden anomaly in the Baltic required disciplined survey work and modern instruments, not blind dragging. Instead, his team launched a methodical forensic search designed to let sensors, never not luck, strip away the seabed. The search zone was immense. Based on extensive archival research, the team laid out a precise search grid covering a massive area of open water nearly 4 miles off the coast. To systematically cover this blank canvas, the survey vessel performed a grueling maneuver known as mowing the lawn. The ship drove in perfectly straight, parallel lines, turning at the end of each transect and returning on a slightly offset heading. This tedious process ensured that the electronic sensors achieved overlapping coverage of the seafloor, leaving no blind spots in the primary search zone. The success of the entire campaign rested on maintaining a constant speed and a rigid heading regardless of surface weather or ocean currents. The primary instrument deployed for this digital resurrection was the side-scan sonar. This device fundamentally changed how humanity interacts with the deep ocean. The mechanism relies on acoustic anomaly detection. A heavy, torpedo-shaped towfish is lowered on an armored cable and flown just above the seafloor. As it glides through the dark water, it continuously fires high-frequency sound waves laterally across the clay bottom. These acoustic pulses travel swiftly through the dense, cold water, strike the seabed, and bounce back to the receiver. The genius of the side-scan sonar lies in how it interprets these returning echoes. The natural floor of the Baltic Sea consists of soft, flat clay. This porous mud absorbs most of the acoustic energy, returning a very weak signal to the towfish. However, when the sound waves strike a hard, dense object like an oak timber or a buried bronze cannon, the signal bounces back sharply. Furthermore, a solid structure standing proud of the seabed entirely blocks the acoustic pulse from traveling further. This creates a distinct acoustic shadow on the far side of the target. By measuring the length and shape of this dark void on the readout, surface operators can accurately calculate the height and complex geometry of a submerged object without ever placing a diver in the water. To verify any acoustic targets, Franson also deployed a marine magnetometer. This highly sensitive instrument measures microscopic local variations in the magnetic field of the Earth. While the side-scan sonar painted a topographic map of the physical debris, the magnetometer hunted for the invisible magnetic signatures of massive iron anchors, cannonballs, and structural bolts buried deep beneath the mud. Operating these two distinct sensors simultaneously provided a comprehensive diagnostic view of the alien environment below. The relentless grid search finally yielded a definitive result on August 8, 1980. After days of blank returns, the instruments logged a strong target, a hard anomaly, and a broad scatter pattern where the clay plane should have been uniform. When the team reviewed the fresh records, the site aligned with the archival case for the lost Flagship, yet the shape was wrong. What emerged was not a clean silhouette, but a confusing spread of structure, a debris field that refused to read like an intact shipwreck. The geometry of the shattered hull on the Baltic Sea floor presented a massive physical trap for the investigating dive teams. When researchers finally descended through the dark water to visually inspect the site, they did not find an intact 17th century warship resting peacefully on its keel. Instead, they were confronted with a pulverized landscape of shattered oak and twisted metal. Built as a tall, top-heavy artillery platform, its sheer mass was enough to pancake the central and aft sections heavily into the soft clay. However, the extreme fragmentation of the forward section could not be explained by simple impact forces, the crushing weight of the artillery, or 3 centuries of slow biological decay. To decode the true mechanics of the disaster, marine archaeologists had to read the physical trauma etched into the surviving timbers. A massive wooden ship breaking apart at a depth of about 26 meters will usually show signatures shaped by gravity, sediment load, and the slow degradation of fasteners, not the crushing regime of true deep water. In many wrecks, heavy timbers slump inward or settle outward as bolts fail, and the structure relaxes under its own weight. The forward wreckage of this Swedish flagship exhibited the exact opposite pattern. The heavy oak frames and the thick outer planking at the front of the vessel were violently peeled outward. The raw, splintered edges of the wood fibers indicated a sudden, catastrophic shear failure rather than a gradual separation. This specific radial pattern of destruction was strongly consistent with a confined magazine detonation. In the late 17th century, volatile black powder was the sole chemical propellant for naval artillery. It was stored in massive, tightly packed quantities deep within the lowest decks of the hull, deliberately placed far below the waterline for protection. The architecture of a first-rate ship of the line was intentionally designed to resist incoming solid iron round shot. Its sides were built from deeply reinforced oak, often layered several feet thick, creating an incredibly rigid outer shell. However, this necessary defensive strength inadvertently transformed the forward section of the hull into a highly efficient, heavily contained pressure vessel. Inside a sealed magazine, black powder does not simply burn, it turns confinement into a weapon. With the bow built as a rigid shell and nowhere to vent, the shockwave had only one outcome: an internal overpressure fracture that ripped through reinforced decks and side timbers in a single violent pulse. The proof of that failure was written into the seabed itself. Site mapping showed the starboard bow was not merely broken, it was but blown clear of the main wreck. Massive, deeply reinforced sections of the forward hull were found scattered far from the primary wreckage mound. The sheer mechanical force required to shear these massive timbers and throw them laterally through the dense, heavy water column was staggering. By precisely tracing the trajectory, distance, and orientation of these blasted wooden fragments, researchers could draw converging lines back to a single geometric origin point deep within the forward hold. Every shattered beam and outward-facing splinter perfectly confirmed the violent reality of the final moments. The heavy outer planking was shredded outward, and the massive internal support knees were snapped cleanly in half. Careful site mapping of the scattered starboard bow aligned with the physics of a confined blast, they finally giving shape to the ship's chaotic last seconds. But the seabed held more than timber, and recovering that record would require a different kind of excavation. The clay bottom of the Baltic Sea did not just hold the shattered timber of a lost warship, it preserved the violent biological reality of a massive detonation. When modern dive teams laid a numbered excavation lattice over the debris field, they were not merely lifting degraded bronze and iron. The excavation methodically peeled back centuries of compacted mud to reveal over 30,000 distinct artifacts. But the most critical evidence recovered from that lightless seafloor was not manufactured from wood or metal. As the underwater vacuum lifts carefully cleared the sediment layer by layer, researchers uncovered an immense concentration of human skeletal remains. The dense, oxygen-poor environment of the seabed had locked the violent final moments of the crew perfectly in place. Retrieving a substantial quantity of human remains required surgical precision in a deeply hostile underwater environment. Divers operated highly calibrated water dredges to gently suction away the surrounding clay without disturbing fragile biological evidence. Every skeletal fragment was meticulously logged within a three-dimensional reference frame before being brought to the surface. Once secured in the laboratory, the bones were subjected to a rigorous scientific process known as forensic osteology. This specialized discipline focuses on reading the structural history of bone to reconstruct the precise mechanics of a physical trauma. The immediate challenge was distinguishing between damage caused by 3 centuries of slow degradation in a marine environment and the instantaneous forces exerted during the sinking. The exact state of the microscopic fracture lines had to be carefully isolated from natural biological decay. A human bone submerged in seawater for centuries will naturally undergo structural decay. The mineral matrix weakens, and accumulating sediment can impose slow compression fractures that mimic damage. But in this crew's remains, researchers repeatedly identified perimortem fractures, breaks laid down at the moment of death, more consistent with sudden, high-energy force than with gradual post-deposition crumbling. In the confined spaces below the main deck, a blast wave would have driven pressure through compartments like a hammer. Because the human body is largely water, it is brutally vulnerable to rapid spikes in external pressure. Long bones, ribs, and skulls can shatter in an instant. The jagged, unhealed edges showed no sign of recovery, immediately fatal damage that echoed what the shattered timbers already implied. By mapping the specific distribution of this perimortem bone trauma across the established grid, archaeologists could trace the precise path of the destructive energy through the populated compartments. The remains positioned closest to the forward blast zone suffered total biological obliteration, leaving only heavily fragmented pieces. Meanwhile, those stationed further aft exhibited sheer trauma consistent with the unstoppable kinetic wave tearing through the length of the hull. This forensic biological data provided a perfect, independent verification of the catastrophic forces involved, entirely without relying solely on the surviving timber structures. The meticulous laboratory analysis transformed anonymous skeletal fragments into a highly detailed diagnostic map of a 17th century event. Every bone cataloged and every shear fracture recorded added a crucial layer of absolute physical truth to the historical narrative. The systematic extraction of the physical and biological evidence from the sea floor achieved what no archival document could ever provide. The extraction grid yielded tens of thousands of items, systematically closing the forensic gap left by the 17th century disaster. The true measure of a deep water site is defined by what the original operators chose to leave behind. In the late 17th century, the Crown demanded an immediate return on its lost military investment. The primary directive was not historical preservation, but absolute financial recovery. The state authorized a brutal, high-risk extraction campaign solely to reclaim the heavy bronze artillery. This singular focus on immense military mass meant that the moment the 60 massive guns were winched to the surface, the site was functionally abandoned. The authorities flipped their operational status from an active salvage zone to a closed maritime grave, leaving thousands of unseen fragments buried in the Baltic mud. The final yield of this dual-era operation perfectly illustrates the shift in human engineering objectives over 3 centuries. While the early salvage teams maximized their haul of bronze, they ignored the shattered architecture and the personal equipment of the crew. When modern researchers finally breached the site, their objective was entirely forensic. By establishing a rigorous underwater grid, they successfully cataloged and raised more than 30,000 individual artifacts. This staggering volume of material transformed a stripped military wreck into one of the most densely mapped archaeological matrices in the region. The last layer of this success story was what the mud kept. The crew themselves. Extracting the physical hull and the military hardware was an exercise in industrial lifting, but retrieving the shattered crew required surgical discipline. The modern excavation recovered a substantial quantity of skeletal material from the suffocating clay. By applying advanced laboratory analysis to these fragments, scientists documented trauma consistent with catastrophic forces during the sinking and breakup. This biological evidence reinforced the picture, adding a human record to the physics already written into the wreck. The legacy of this Swedish warship is defined by its absolute resolution. Very few deep water disasters offer a completely closed circle of evidence. The primary military assets were successfully salvaged by the very civilization that built them, pushing the limits of early mechanical engineering. 300 years later, the precise mechanics of the sinking, the explosive destruction of the hull, and the biological fate of the crew were perfectly reconstructed by modern science. The dual operations effectively decoded the site completely. The freezing cold zone of the Baltic Sea acted as a perfect, impartial vault. It surrendered the heavy bronze to the survivors and preserved the absolute truth of the disaster for the modern era.